next set of videos, we're going to be talking about triacylglycerides. Triacylglycerides are also known as our energy stores, so it's what we think about when we think about like adipose tissue and energy stores and fats and things like this. So the basic backbone, if you notice in our little flow chart here that you have on the slides, is glycerol based. So glycerol, right, if you remember from organic chemistry chapters, OL stands for alcohol. So a triacyl, so a tri, 3, so we have 3 carbons in glycerol. So 3 carbons, each of which has one OH group. So the acyl part of this, so we have 3. Acyl is a type of linkage, so glyceride or glycerol or triacylglycerols, they are the same thing because we need 2 names for the same thing. An acyl linkage is essentially a C double bond O to another oxygen with the R group. So, or if you remember, this is also known as an ester, but in biochemistry we call them acyl groups. So if we take a look, that nomenclature that we talked about for fatty acids, you use that if you say, oh, I have a triacylglyceride with, let's say, a 16-0, a 14-0, and an 18-1 delta 6, we could now draw this particular triacylglyceride. So if we take a look, we just need to go back and talk about that triacylglyceride and how we name these particular species. So again, these are triesters of glycerol. So remember, an ester linkage, right, we will essentially get rid of the hydrogens here, okay? And our fatty acid, therefore, will be C double bond O. So this is very similar, this group here, this comes from, if you remember, in fatty acids, we have our carboxylic acid. That is this group essentially that is coming here. So oxygen, carbon, double bond, and then the rest of the species here, okay? So if we were to draw this as a 14-0, this would be carbon 1, and then we could draw 12 more CH2 groups, so that's 13 carbons, followed by a CH3. There is our 14-0 that's on there, okay? And then you could do the same thing by drawing a C double bond O, followed by, in this case, if we're drawing the 16-0, we can have 2, that would be 15 carbons, make sure you always count this carbon, and then 16. If you don't necessarily feel comfortable drawing it like this way, you can also just do it with the skeletal structure, right? So again, carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we know that delta 6 means we're going to start here with carbon 1. 1, 2, 3, 4, 5, 6. Boom. We have drawn a triester or a triacylglyceride with a 14-0, 16-0, and 18-1 delta 6 fatty acid tails. So again, you should, that's why we do the fatty acids first, right? Given this particular type of nomenclature or with the omega nomenclature, you should be able to draw a triacylglyceride. So again, this part is always the same. It's always 3. You're going to have 3 fatty acids that are specified there. So you can see in the slides from your book, you have glycerol. You take 3 fatty acids. In this case, they took 3 16-0s, and they just added them on to make those esters as you break them down. So in our bodies, like if you eat things, you know, like avocados or things that are high in fats and stuff like this, right, we have a bunch of enzymes called lipases, L-I-P-A-S-E-S. So remember, anything that ends with ACE means it's an enzyme. These are enzymes that break down fats because your body may need those when you eat them. As you're making more cells, you need more lipid bilayers, or it may choose to store them, whichever it is. So again, you might need those types of enzymes in your digestive system. They're stored off, usually like in your gallbladder, or you may have heard of like bile and bile salts. There's a combination of things and enzymes and stuff also secreted by the pancreas that can help with this. So again, triacylglycerides, we do not find them in membranes. They are only found for energy. Okay, so here is a practice for you. So rather than the one that we just did, I'd like you to do this one on your own, but you can draw a triacylglyceride, okay, with the 3 fatty acid tails. And in this case, I give you both of the types of nomenclature. First of all, I give you a 16-0. So no double bonds in that one. However, the other 2, we have an 18-1 omega-3, so you're counting in from the omega end, 1, 2, 3 to draw that double bond. But then there's also one with 2 double bonds. And this is using the delta nomenclature where you start with carbon number 1 and follow that through to carbon number 5 and carbon number 8. So if you have questions on how to draw this, please send me an email, or you can stop by my office or phone call, Zoom, etc. to meet with me if you want to go over this. All right, but let's assume that you got that practice down. So now let's talk about membrane lipids. So now that we've done triacylglycerides, now here's the difference between membrane lipids. This is generally, membrane lipids are mostly what we think of when we draw those little cartoony guys where we have the head group and we have 2 tails. So if you notice, a triacylglyceride has 3 tails. Well, in a membrane lipid, we only have 2. So the difference between a triacylglyceride and these membrane lipids that we're going to be talking about is we actually take away one of the fatty acid tails and replace it with what we call a head group. So these are the tails, and then the head groups would go over on the other side. Okay, so head, tail. Now, it doesn't necessarily matter if you draw the head over here or over here, but you should know that there's a difference between the fatty acid tails and then the head group. So again, a membrane lipid, 2 tails, 2 fatty acids, 1 head group. So that's why we draw the little squiggles. There's only 2. That is actually by design, and that's actually biochemically accurate. Okay, so this is what we think of when we think of these. So remember, these guys, we have a polar head group, and we have a non-polar fatty acid tail. So this is what we call an amphipathic molecule. So this basically means both loving. So both meaning in the environment of either polar or non-polar. So we have both a polar that loves to be near polar things, and we also have a non-polar area that loves to be near non-polar things. So that's what we're going to be looking at when we start talking about membrane lipids. The 2 types that we will talk about are designated by their head group. So you have 2 types of head groups that you can have. You can have a phosphate, which is polar. So therefore you would make a phospholipid, or you can have a sugar. A sugar, remember, has a lot of OH groups on it, so it's very polar. So again, you can either be a phospholipid, where your head group is a phosphate, or you can be a glycolipid, where your head group is a sugar. And so now that we know the structures of sugars, we should be able to draw and identify those. Within phospholipids, and these glycolipids, actually both of them, we can either have glycerol as the backbone. So again, 2 tails, and then a head. You can put either the phosphate group on one of those head groups, or we can have something called sphingosine. So we will talk about the structure of sphingosine in a bit here, but sphingosine already has 1 existing tail. But sphingosine is a very common known backbone for a lipid. So if you've ever heard of ceramides, if you've ever seen those commercials for CeraVe, they say the ceramides in CeraVe, they talk about how that's moisturizing. That's actually accurate because ceramides are a sphingosine-based backbone that we talk about with lipids to help hydrate your skin. Okay, so again, glycolipids, 2 plus a sugar. Phospholipids, right? So within this phosphate group here, we are going to have 2 types. So with a phosphate, you can be glycerol-based, just like we've been seeing, or you can be sphingosine-based, which we will draw and show in a minute once we get to these sphingosine-based backbones. Okay, so this is what we will talk about next. So we're going to continue because we've already talked about glycerol-based for the triacylglycerides. We will talk about glycerol-based phosphoglycerides. So again, these are the common ones that you would see in a cell membrane. You are going to have 2 tails, and then 1, in this case, of a phosphate group. So all we would essentially do is we are going to take our triacylglyceride and we will basically get rid of 1 of the fatty acid tails, okay? And we would replace that fatty acid tail with a phosphate group. And that phosphate group, OR. So if you notice here, it's a negative charge, lots of oxygens. Now this is now a polar group. So here's our polar head group, right down here with the phosphate, and our 2 fatty acid tails. That is literally the only difference between a phosphoglyceride and a triacylglyceride. So again, if you know the structure of how to draw fatty acids, you know how to draw a triacylglyceride, and now you also know how to draw a phosphoglyceride, okay? So again, this is just from your book. It shows you the little diagram that they have to show how these are related. So again, here's our 3 fatty acid tails, okay? Glycerophospholipids or phosphoglycerides. So again, if you notice, there are many different ways to say these, but they just have to have the constituent parts. Phosphoglyceride shows you glycerol with a phosphate. You can also say glycerophospholipids, glyceride, glycerol is the backbone, phospho for the phosphate in that case. But if you notice in that membrane lipid, 2 fatty acid tails and then a phosphate group with some other potential group that's an R group here, okay? We'll talk about sphingolipids here in a minute, but we will just leave those for now. But the main thing to take away is this is technically now a monophosphate, mono 1 phosphate, diester. So ester here, instead of a C double bond O to an O like we have up here, and here with the fatty acids, it's a phosphoester. So it's an ester, but you just replace the carbon with a phosphate instead. Okay, so here's an example, glycerophospholipid. So these R groups that we have here, there are 3 main ones that we can have. And what's kind of nice is they're kind of named based on what they are. So when you're looking at this R group, one of the R groups that you can have is called ethanol amine. So ethanol is 2 carbons, okay, with an OH group. So you can imagine this is the OH group that's attached to the phosphate. Ethanol, and then amine is just NH3 with a positive charge. So this would be a phosphatidyl ethanolamine, okay? If you replace, and here's the way I remember this, so ethanolamine, based on that name, right? Ethanol here, eth for 2 carbons, enol, the OL group tells you that there's an oxygen at the end here, and then the amine group here is NH3+. Because that helps us, we have polar with the oxygens here, but also we have polar with this positively charged amine group, okay? Now, that's the first head group that you should know. The other one that you should know is choline. Here's the thing, choline, if you notice, begins with a C. So all that you're doing, easy way to remember this, is you're going to take ethanolamine, but you're going to replace these H's here with C's. So literally the only difference between phosphatidyl ethanolamine and phosphatidylcholine is that at the very end here, so to turn this into choline, you would just take that nitrogen and you would make 3 methyl groups. So you just add the C in there. Choline, C, you add carbons instead for the rest of that group. And then finally, the last one is phosphatidylserine. So serine is literally, you're just adding the amino acid serine. Now we have not talked about serine yet, but I will draw the structure of serine so you know. But if you notice, all of these have an OH group at the end. So if you look at ethanolamine, OH group, and OH group, okay? These are the OHs, they always go next to that phosphate, always, 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 okay? So serine, the structure of serine, the OH group that we have is right here. The rest of the molecule, which we will get in the next chapter, right, if you notice, still has an NH3 group, but it has a COO- as well, also keeping us polar. So this oxygen here is the oxygen that would go down here, and then you would draw the rest. So you should get some practice with drawing these particular glycerophospholipids. Those are the 3 combinations that you can have: ethanolamine, choline, or serine. And then you should be able to draw the fatty acid tails on these 3 carbons. So there's 3 carbons, 2 have fatty acid tails, 1 has a phosphate, always the same, and then an oxygen here connected to the rest of whatever that group may be.